Let me do my worst. vNUMA, what does it actually mean? I'm Wim ten Haven. I'm working for Oracle in the Oracle Linux virtualization engineering team. And this is a team which adds to Linux development. We do upstream development. We backport a lot of upstream development, and we support various groups in Oracle for databases and other related products. This is not my slide, but it is a slide. So this is the agenda. Before I go into what does vNUMA actually mean, or vNUMA, what is it good for, I'd like to inform you a little bit, or talk a little bit about virtualization, system architectures, uniform memory access and non-uniform memory access. I'd like to enlighten you on host topology and processor topology with respect to processor topology and NUMA topology. And then the key part of this presentation is partitioning the NUMA host. And finally, a mechanism I'm preparing to upstream sometime sooner, named vNUMA automatic host partitioning. Why is virtualization useful? I'm not sure if are there people in this audience who have used virtualization? How can I ask? So are there people in this audience who use Lipfird? People directly from KIMU? Oh, all right. And I assume all are on KVM, or are there Zen addicts in this audience? Okay. Well, I don't have to explain you the benefit of virtualization then, but and the need for virtualization. Oracle uses virtualization for various cloud offerings like Oracle Cloud Infrastructure. I'm consulting a team which is called Exadata, and we make a product called Cloud in a Box. It's basically a cloud within the corporate environment. So the terminology is, there's a couple of components I'm going to address in this presentation. It's about kernel-based virtualization machine, KIMU, which stands for Quick Emulator. KIMU can actually emulate any CPU, but it can also, in combination with KVM, utilize the kernel support, hypervisor support within the host kernel to get your code running. And Lipfird, this is the area or the component I like to talk about, is an agent or a management infrastructure to partition hosts, to manage the guests, and all kind of things, specifically to that guest. And then there's a host and a guest definition. Well, let me go to the big picture. On the bottom, bare hardware, KVM kernel, and to the left you see, on top you see three slices which define the machine: user slice, system slice, and machine slice. The machine slices are typically the guest or the guest virtual machines you are running, and user slices, these are processes on the host which may be around for any purpose. It could be a shell, but it could also be a system administrator who is administrating the guest via a command line interpreter called First, or he can do it by a Virt manager, a graphical user interface tool. And under the system slice, there's a daemon called Lipfird, which is which started out as a library, but it is a system service. It's a daemon under Unix systems, which manages various KIMU processes, or Zen. It may have hooks to Zen hypervisor via a DOM0 kernel to control the guests themselves. KIMU is the actually virtual hypervisor thread manager and the instrument which hosts your virtual machine. these are a couple of high-level parts of, these are a couple of parts of Lipfird which I placed on the slide to inform you why you should use Lipfird. I mean, you can directly use a KIMU to control your guest. It's very inconvenient, and I believe KIMU has something like, well, it has more than 1,000 switches, command line switches, to achieve things. Lipfird is relatively easy to start working and operating virtual machines or guests. And Lipfird allows you to program the guest with XML, or you can describe your virtual machine in XML. And you can also connect to Lipfird from various network environments, or also directly by various application programming interfaces. And Lipfird you typically use if you have to manage the life cycle and the configuration of many guests simultaneously. Another benefit of Lipfird is that it has a very good single point serial console mechanism. Like if you take VirtualBox, for example, these are all virtual management utilities which pop up graphical user interfaces, allowing you to do all kinds of things. But you always need a graphical user environment to make things happen. With First and Lipfird, you can actually connect yourself in a serial fashion to a virtual machine running somewhere in the world or on your machine. This picture illustrates how Lipfird should be seen between its management tools and between the hypervisors on the bottom. Lipfird operates on a hypervisor local to it on the machine where it is running. So if Lipfird is managing guests on in a Zen infrastructure, then Lipfird communicates directly, or not directly, but indirectly, via a domain called DOM0 with the hypervisor, the Zen hypervisor. And if it is running on a Linux kernel KVM environment, then it's running on the host, which was seen in the other slide. But Lipfird can also connect to remote hypervisors. You should see it as a client. You should see Lipfird as a client in a client fashion to the other remote Lipfird daemon or service. This is the high level how such a connection works. Like Fish gives a command to Lipfird. This is a shell. Maybe in the end, if there's some time left, I'll give you a small demonstration how you connect to a KVM hypervisor using Lipfird. But Lipfird first gives a shell, and it allows you to give commands towards Lipfird. If you under this first command, you can give the help command, and there's somewhere close to 260 different commands where you can edit domains, configure domains, dynamically configure domains, start domains, stop domains, shut down domains, destroy domains, and migrate domains. That's one of the important things of virtualization, I think, is that you want to migrate something from an existing environment to another machine. And Lipfird, under a KVM construction, spawns at the start of a guest the KIMU process. This is an ordinary Unix process. The KIMU process will arrange for the memory for the guest, and at some point it knows the guest description, and it will allocate the hypervisor threads and start the guest under the hypervisor by booting the guest kernel, and the guest kernel will bring the guest environment to life. And after that is done, Lipfird can connect or talk with KIMU by QMP, and this is a JSON. This is a protocol based on JSON. The communication is done network-wise between Lipfird and KIMU, where Lipfird, under request of a user tool, can spawn additional or hot plug additional CPUs or hot plug memory or give APIC commands to shut down or whatever. There are other utilities, like First is an absolute shell environment, but there's also FirstInstall, which allows you to quickly provision a new guest machine. So you can, with FirstInstall, give a command line to create a guest domain with a name, and you can ask it to give the guest domain 8 GB of memory and 16 CPUs. And you can tell it where it should boot from the ISO image, and you can also tell it what the disk what the disk path it should utilize. You can tell it to be quiet. You can tell it to do all its setup from a script or connect to a shell. Virt Manager is more advanced. You get a nice graphical user interface, and you can click yourself through the configuration, at some point launch the guest and have it running. And Virt Viewer, that is a graphical console which can be splice or VNC enabled. And you get the ordinary PC graphical VGA or XGA or whatever card. Then the system daemons, VirtD and then VirtLogD. Well, VirtD is this process which is doing the management of the guest, and VirtLogD is a process which logs all actions that happened and errors that happened under guests. If there are warnings, errors, or security violations. And KIMU, which is the quick emulator. On architecture. Well, in the past, machines started out with a single processor. At some point, companies started to create multiprocessor machines, beginning CPUs and IPU configurations. Later on, multiple processors on a bus, and at some point, even multiple processors or cores within a single chip. I wrote it as processor, but you maybe actually read it as socket. I mean, processor doesn't mean that there is a single CPU within such an orange block. It could also be a couple of CPUs. The key point of uniform memory access is that everything is connected to the memory over a single bus with the same characteristics. There could be parallel path, but the memory and the memory bank 1 is equal to all the processors and equal to the I/O. The advantages for uniform memory access is that all the processors share the same memory, the timings are the same, peripheral timings and peripheral access is same in some fashion, and it's a relative easy programming model. There is a problem if you start to add more processors in case you need more CPU power, then you run into a problem of bus contention. And you can say that unified memory architecture is in some uniform memory access is in some fashion distilled from software needs, and software availability came from NUMA in return. In the beginning, you typically noticed like heavyweight processors where different processors communicated with each other over a shared memory, System 5 shared memory pool. Later on, lightweight processors with native threading came around. These are typically used in database engines, Java VMs, low-level virtual machines, and there's a whole set of libraries you can utilize from your programming environment as well. But ultimately, the big programs started to outweigh the UMA architectures, and they were rooting for NUMA.
Why would you be rooting for NUMA when from a systems perspective, NUMA does what you need it to do?
Well, very high-end databases bring all kind of components into the game, like a Java virtual machine, and you run into the bus contention. So you need more processor power, but there is no possibility to add more CPUs or sockets to the machine, to the bus. So it rooted for NUMA is that what hardware manufacturers started to do is to come up with this design where you have, well, actually, like this is a UMA entity, and this is a UMA entity, and this is a UMA entity, and this is a UMA entity. But they interconnected the UMA entities with each other, so that the database engine, for example, can run on this entity, but the database engine is communicating with the Java virtual machine in a shared memory fashion, a System 5 shared memory fashion, which is running over here. So you have fast performance for the memory. It's faster than network performance for the memory. But there is a problem if you... no, I come to that later on. The software is very oriented to the NUMA architecture. Like your database typically runs here, your Java virtual machine runs here, your low-level virtual machine may run over here, and all the other users are run over here. Everything is interconnected. Everybody uses each other data. So if a processor if a core on processor 1 needs to access memory on this processor's local memory, it can do that, but it comes with a cost. Because it is remote, the memory is remote to the processor. I do not know exactly what the differences are in timing, but like I've been playing with it. There's a local memory access which we define by a local cost of 10, which means local. It is instantly there. And if you go remote, you have a distance of 2.21, which comes with a cost of 1.4. So every cycle takes 1.4 of the time of your local setting. But non-uniform memory access, like are there advantages? In my vision, there are no advantages. There is only disadvantages. So maybe that answers your question. But the advantage is that you can expand your machine, and you can bring more software in the game for the big process you're running. And the disadvantages are typically cache coherency if you cross buses, and if you need to access the remote memory, it comes with a cost because the memory cycles are slower, and other CPUs may actually give you contention. They may have priority over your cycle. So you'll definitely measure this if you definitely be able to measure the differences. And multi-threaded programs, if we go back to this process, like multi-threaded processors should always stick to a node within the environment. Like, never have a Java VM which starts to run threads on another processor outside your thing. It's very bad for performance. So what it is good for? Well, vNUMA, this is the problem. Like, okay, we have software, like Oracle, they have big database engines, and this software did outweigh the UMA architectures. NUMA came into the game. The software was molded in a way that it did fit the NUMA architecture. And then suddenly people start to virtualize the environments for the cloud. And they move these database environments into those cloud virtual environments. And yeah, they're back on the NUMA architecture initially. So you need to describe your guest in a vNUMA fashion or in a virtual NUMA fashion. And that's where I like to talk about. Let's take a typical Sun machine or Oracle machine now. these are the processors, and these are sockets, and these have, for example, 30 threads each socket. They're equipped with a lot of memory, local memory, and they have all their own PCI subsystems. So bringing an application to such an environment in a virtual NUMA concept, you need to take a look at this picture. You need to look at the high-level design of the machine. So what memory is local to this processor and to that processor, and how is the I/O arranged? Like the PCIe controllers under this processor typically serve the disk drives, and PCIe controllers under this processor typically serve the network connections. And there are PCIe connectors over here, but there's nothing in it. Now, before we can create or describe the vNUMA topology, we need to instrument, or we need to describe the architecture of the host machine, and that can be done with a couple of commands like lscpu and lstopo. lstopo is a very powerful package. It comes from the, it's a very powerful command. It comes from the HWLOC package with a whole set of other commands. And it allows you to generate an XML description of the host machine, or also an ASCII description of the host machine, but it can also present the host machine in a graphical fashion. And but you can also inspect the host with the help of Lipfird by utilizing a couple of the host commands. You have the help command. You can give a help host command, and it describes all the commands which are available for the host. And from there you can make a view on how the host is arranged, what kind of CPUs there are within, how many cores there are per socket, how many threads there are under each core, what the distances are for local and remote host, etc. And the device lists. And you can even dump out XML descriptions of devices. lscpu on the host describes the CPU topology, the processor topology, and I also have shown a command like lstopo, which gives you the HWLOC package description or a graphical outfit of one of the sockets on the host. So that socket or this NUMA node has this processor. Here's the NUMA description. And the high-level software, which is taking advantage of NUMA architecture, internally have utilized libraries which are doing the NUMA CTL to get informed on the host NUMA topology and lscpu, or they directly examine the /proc CPU info and interrupt info to get an understanding like, this is how my host looks like. So this is where I/O controllers are. This is local memory, this is remote memory. And if I start using multiple cores under a threaded environment, I should keep those cores together because they are under the same node. So we now know how the NUMA host looks, and we are going to create a guest, and we are going to render a vNUMA architecture of that guest, of the host into that guest. Earlier I mentioned the FirstInstall command, and that FirstInstall command you can give it a couple of arguments which are important here. Like you can tell it this is the guest name or the guest domain name, and I want you to equip it with 32 gigabytes of memory, and I want you to give it 16 CPUs or virtual CPUs, and I want to base the guest on a Q35 architecture. There are two architectures supported by Lipfird. That's the i448FX chip architecture, which is backdates till the year 2000, I believe. That's where it was stopped. And then the modern architecture is the Q35 architecture. If you start creating guests, I advise you to operate on Q35. You only may need i44FX architectures if you have Windows running in guest, which require legacy devices. And you can give CPU mode. I advise you to set it to host pass-through, because if you want to do vNUMA, why? You want to create a guest which is a replica of your host. So you want to give it the same CPU architecture as available under the host itself. You can also give a CPU model there, and you can even enable and disable features, and that is only in the interest if you are going to utilize guest migration, where you migrate from from between different CPU architectures. Like that's where you have to restrict to the least complex architecture in your environment. So this guest is generated in XML, and I'm booting it. And this is the guest actually running, and well, it has the 16 CPUs. It mentions like there is no NUMA configuration found in the kernel buffer. And there is something peculiar here about it. It has 1 thread per core, and it has 1 socket per core, and it has 16 sockets. That's very odd. The CPU model did arrive correctly. It is based on a KVM hypervisor. And well, it tells me, like, if I'm inspecting the NUMA architecture, that there is only 1 NUMA node available, and all the CPUs, or all the vCPUs, are under that NUMA node. And it has the 32 gigabytes of memory. So we need to work this. So the first thing you can do is dive into the XML of the guest, and you can do that with the first edit on the guest domain. And you can specify the topology of the processor. That is something that is not automatically done by Lipfird. So you have you can specify, well, my host has 4 sockets, it has 2 cores, and it has 2 threads per core. 4 times 2 times 2 is 16. And booting that guest with the new CPU topology definition, the guest will reflect like I have 2 threads per core, 2 cores per socket, and 4 sockets per host, but a single NUMA node. There's no NUMA configuration found. So the next thing to do is to get back into the XML of the guest and describe the NUMA topology. And well, let's say we equally balance the amount of processors. We have 16 CPUs, so I think it is fair to give every NUMA node or cell ID 4 vCPUs, and give them 32 divided by 4, 8 gigabytes of memory. And so, something additional you can do is to describe the distances. Like if you don't describe the distances, Lipfird will conclude that the differences are local and remote, and local is 10 and remote is 20, whatever that may be, but software may find out what it means. But you can also give it a value, which is the actual distance, and software may recognize the certain timing settings for that, and knows what the costs are if you access a local, a remote or a local host. Booting that machine comes up with 4 NUMA nodes describing the vCPUs per NUMA node, and the NUMA CTL.H gives you how the vNUMA machine is rendered. So at this time you can think, oh, I'm done. Like I have a guest. It is a NUMA guest. I have CPUs equally balanced over the vNUMA nodes. I have memory equally balanced over the vNUMA nodes. I'm done, but that is not true, because there is nothing in this picture describes like what CPU under the guest is assigned to what memory under the host, or what CPU is assigned to a specific CPU under the host. So for that you have to describe the pinning. And I have to go back to the LSCPU. Important here is that if I did an LSCPU on the host, it tells me that NUMA node 0, NUMA node 0 has these CPUs, or physical CPUs, assigned. And let's take the image for node 2, which is illustrated over here. It has 30 to 44, and a group for 90 to 104. And 30 and 90 are two threads under the same core. So it is very important under the guest to keep that consistent as well, because the guest software, which is utilizing the vNUMA architecture, will definitely start looking in how the CPUs are arranged and bring them together for optimum performance, because they share the same cache. So for that, we pin the CPUs. We say 0, 1, 3, and 4. We fit under the CPUs on the NUMA node 0, and 4 to 8, 7 under 1. And I hope the colors illustrate what matches what. And that is, if you then inspect the guest, and there's a utility under First called vCPU info, then you will see that what vCPU is assigned to a pCPU out of a pool, and that is the range. These are the ranges for P0 or socket 0 or NUMA node 0. These for 1, 2, and 3. But anytime a CPU is utilized, it may just, the hypervisor may just pick one of the available physical CPUs in that pool. And for that, this is something you can actually manually describe, like put CPU, vCPU 0 under a pCPU 0 and 1 under pCPU 60. And that is nice, but if you have to do that for one guest and the other guest adjacent to it, you have to create a very complex schema, like what is assigned to what? It's almost impossible. So we had a customer in Oracle Exadata, and this was striking them in performance. And we made a small design change in the KIMU driver under Lipfird, where we said like, okay, like if we render a pCPU from this set, then pin one of the physical CPUs automatically to that vCPU, and we know what the sibling which is under the guest, so we have to automatically find the sibling pCPU under the guest as well, and then you get a one-to-one mapping. So you can manually describe this in your XML for the guest, but if you have many guests, it's almost an impossible task. Then you could also automatically do that, and that is something I'm working on to upstream sometime. So the pCPUs are defined now. The pCPUs are fine. And we are guaranteed that the physical vCPU under node 0, under vNUMA node 0 is matching its NUMA node 0 pCPU. And the same needs to be done for the memory. If you do not describe what memory comes from where, then Lipfird is originally good for you. It tries to create the picture itself, but if this is impossible, it just gives you some memory, and it may be a very bad description. So to avoid that, under the XML for the guest, you can tell it to utilize a mode strict. This has a penalty, because if you have many guests under a host and the picture doesn't fit anymore, then you have to give up. That it doesn't work anymore. But for initially, this will work fine if you allocate the memories in a strict fashion for the node. So we have the CPUs done, vCPUs done, we have the memory done. We have a NUMA guest. You could basically say that you're done and everything is good, but that is not true because you still have the I/O, and those applications which utilize a NUMA architecture on the host will definitely do the same under a vNUMA environment. So you also have to describe the host architecture in the node virtual layout. If you don't do anything, you basically get this picture. So any PCIe root port available for you to insert an interface to, and that could be a disk controller, it could be a network controller, or whatever controller, will basically be under the control of the hypervisor, and it will be connected to the first CPU available in the host under any of the nodes. But like our network controllers in the top level picture of the Sun machine were under NUMA node 1, and we typically want all the network operations to happen under the CPUs under the host, which are in our virtual machine under vCPU 427. So for that we have to describe an expander bus architecture under Lipfird in the XML. And well, we give it a bus number, and this bus number gets a node assignment. And it is some way that the KIMU instructs the hypervisor that all the IOs which starts to happen for an interface under that bus are connected to one of the CPUs under that vNUMA node. So we have a bus. Under that bus we need to add a controller or a PCI root port. Sorry, a PCI root port. This is a PCI slot in which you can insert a controller. And finally, we can put our network interface under that controller, under that PCI, our interface controller under that PCI root port by a third I/O driver or a physical driver. And there's various ways you can further optimize this. Like I have gone for bridge, and bridge typically means that the hypervisor will distribute the interrupts for a controller to the physical CPU, and it will also assure that the memory binding and everything is done intact. But instead of a type bridge, you can also do an host def mapping for SRIOV devices, like those new Ethernet controllers. It's a single card, but internally it has like 16 network adapters, which directly map into the guest. So the hypervisor is totally isolated from it. But it needs to be instructed. The hypervisor needs to be told, like, you have to come up with this I/O NUMA architecture and describe where it will interface to. So booting this system again, checking for this PCI bus, it tells me like, okay, you have bus like 254 under NUMA node 1, and under this bus 254, there's a Red Hat Virtuo network device. Okay, and then like, let's take a look like how this XML finally translates into the KIMU command. This is what Lipfird starts the KIMU hypervisor with. And I gotta tell you, you don't do this from a command line anymore. I'm very dyslexic. Even the XML within Lipfird is terrible after a while. So it's like composing all this is already too advanced, in my honest opinion. And finally, it results in this. So I said too advanced. Because like we were thinking, like we have this customer, J.H.A, and they make a cloud in the box offering for corporates, and These are not guests which are described. A customer logs in and typically says like, I need a guest, this amount of memory, this amount of machine, that application that needs to run. So please give me this guest. FirstInstall comes in the game, generates the XML. The XML is imported in Lipfird. Then somebody goes into an editor and starts to edit this guest to make it vNUMA compliant, matching the host. And then 2 hours later, after many mistakes, he starts the guest, and the customer is not happy. So we have been working on a project to make this rendering happen automatically. And we do that by adding an additional XML element called vNUMA mode host. And if that is described in the guest XML, you don't have to do any more editing than telling it like, I have this amount of memory, you need to make it a vNUMA host, you need to make it match the host, and you give it 16 vCPUs, and please do the best you can, and then Lipfird automatically renders the detail on the fly at the moment that it boots the guest. And the guest is fully NUMAfied. And added to that, we've added a couple of other things, like you can do a mode host, but you can also say like, oh, I like a mode host and I like to distribute the CPUs in a continuous fashion, a round-robin fashion or an interleave fashion, or a node-specific partitioning where you say like, okay, like I have a machine which has 4 NUMA nodes and I create a guest and it should only utilize one of the 4 NUMA nodes in the guest. So have my 16 CPUs match the node set node 1 only. There's a catch there because your I/O may not be rendered for the host meeting the host detail, so you won't get this special bus. And then finally, there's a couple of things like what does the vNUMA also do? Like it has to render the hot pluggable mechanisms for if you like to hot plug CPUs. Because that requires additional XML changes. So a customer may hot plug or unplug CPUs, and it needs to be informed like how the hot plugging or unplugging table is done for matching the host. That if you start unplugging CPUs, so this is how the guest was initially composed, and this is how the guest is running the hypervisor threads, 0 to vCPU 15. And then at some point, somebody says like, okay, bring it from 16 vCPUs live to 8 vCPUs, that it offlines not 12 to 15 and 8 to 11. These are 8 CPUs, where you basically leave 2 nodes out of the game. But it should round robin, like take 1 core out or the amount of threads per core out of the game in a round robin fashion if you start offlining CPUs. And the same for memory, like you could also add expanding memory, or well, you can't hot unplug memory because as soon as you hot plug the memory, it's probably utilized somewhere in the guest, and there's no way to get rid of it anymore. But you can describe those memory bars under the vNUMAification of a guest, telling like I have a memory bar and it should go under this node, or even physical memory like NVMe devices or PMEM devices. And an important thing is like you could also use mem-ballooning. In vNUMA, you never should use mem-ballooning. Like that doesn't work because mem-ballooning comes out one big pool, and the one big pool cannot be assigned to one particular host. So you get very strange situations. Okay, so to the left, this is a typical guest. This is a small guest described in vNUMA with all the manual interaction, or the same guest described with the vNUMA mode host topology. And that concludes it.
So we have 1 minute for questions. One question. So if you're using this vNUMA automatic stuff, if you create a second guest, will Lipfird take care to not pick CPUs already in use?
Yeah, yeah. There's like we have done 2 ways. Like you can it initially, you can tell it to utilize spare CPUs. And if all the CPUs are allocated, it will start allocating all vCPUs from the spare pool, from the spare reserve pool, which is very bad for performance for those guests, but it can be done. You can also say, like, well, don't do that, and then at the moment you start such a guest, you get an error message that there are insufficient resources, and same for memory.
Final question?
Did you do any performance comparisons between just leaving out all of the NUMA stuff and including it?
If we have done that? Yeah, no, I haven't done that. I'm working with a speed team, which are doing that constantly, and they operate for the customer. So they come back, and they were also a good quality assurance team because they found, like, occasionally the strange.
But what ballpark are the figures if you run on virtual?
It depends, yeah. Yeah, it definitely depends on the applications, the application stacks they're running. Like I've been for my development work, I was running a couple of benchmarks from Sysbench, memory related, and if you make descriptions of a guest vNUMA where you do not pin the memory to the host memory, you make a one-to-one relation for the guest and their host memory. I could see sometimes things were out of balance in a factor of 2, twice slow, yeah. But you run it again, and then it is 1.4. It was never faster. But if you set it up very accurate, then for those Sysbench benchmarks, you nearly match the host performance. So what I'm saying is, like, you definitely meet the single, the UMA model in a NUMA guest model.